So in the previous video, we have discussed about the comparison between AC and DC transmission systems. So to start with the economics of transmission AC versus DC. In the previous video, we have seen a lot of advantages and disadvantages of HVDC transmission systems as well as HVAC transmission systems. And we have compared whether HVAC is better and or HVDC is better for a particular technical condition. And we have given some justifications for the preference of HVDC transmission. So when it comes for this economics of transmission, so AC and DC both will have the cost involved. So the cost refers here to the investment costs and the operational costs. When it comes for investment costs include the cost of right of way, transmission tower, conductors, insulators, and terminal equipments. So the cost of right of way refers to that of the cost of land requiring for a particular application. For example, if we are planning for a HVDC station, we need to have a particular area of land. We need to acquire that land. We need to build some constructions, building materials. Everything will come under the cost of right of way. And remaining things are easily understandable: transmission tower, conductors, insulators, terminal equipment. And operational costs mainly include the cost incurred due to the losses. Okay, so if here you can see the graph which shows the cost versus distance for a particular AC and DC transmission systems. Here we can see that the DC line starts from here and AC line starts from here. So the initial point refers to that of the initial investment costs. So we call it as terminal costs here. So the AC terminal costs are comparatively less. But in case here you can see the DC terminal costs are comparatively high. So why it is high? AC terminal costs involve only the construction of transformer and the transmission lines, but in case of DC terminal cost, it involves the DC rectifier station, inverter station, everything. So we can say that the initial cost of DC terminal installations will be higher than AC after the break-even distance. So what is a break-even distance? Break-even distance is a distance at which the cost of both AC and DC are same. So after the break-even distance, you can see AC costs are steepest. That means they are highest. But in case if we are seeing DC cost, the DC cost is not that much steepest. It is not increasing rapidly like AC. So after the break-even point, we will always consider the DC to be a transmission system. So whenever we are speaking about transmission, we are discussing in terms of long distance transmission always. In previous videos also we have discussed the same. So when it comes for long distance transmission, we will decide based on this break-even distance. So this break-even distance is depending on various factors like number of transmission towers required and length of the cables, total distance of transmission required, insulators. There are various factors that decides this break-even distance. So usually greater than 500 kilometers we will consider it as the break-even distance. So 500 kilometer and above we will consider it for DC transmission, and less than 500 kilometers it is not viable to invest that much huge amount of cost which is required for the DC terminal costs. And after the break-even distance, AC is comparatively having higher cost. So why it is having higher cost? So the operational cost will be comparatively higher. So that means the losses due to the AC transmission line will be higher. So those losses will also account in the costs. So this is some basic reference which shows the relationship between AC and DC line costs and as well as the terminal costs. And next comes the power transmission tower. So from the diagram itself, you can easily identify which one is better. So this refers to an AC tower and this refers to a DC tower. And here you can see all these things are the number of insulators or conductors required. So just for an example, I am considering 1, 2, 3, 4, 5, 6 conductors are required for a AC transmission system. But in case of DC transmission system, we can see just 2 conductors. It's not only about conductors, it's about insulators, structures required for the transmission tower and everything. And the area required, here you can see the area required for AC tower is somewhat higher, and compared to that of the DC tower it is somewhat less. Only two conductors are used, and again losses will be less. Here six conductors are used. If one conductor is higher, obviously the losses will be more. So obviously when it comes for the distance and transmission tower design, number of conductors, always we will prefer only the DC towers or DC transmission systems. And next comes the economics of transmission. So characteristics of insulator is similar to AC as well as DC transmission, and it depends on the voltage applied with respect to the ground. So the insulator characteristics is always same for AC as well as DC, because this insulator characteristics is depending on the voltage applied, not on any other factors. And second important factor is that for the same insulation level, DC lines with two conductors will be able to carry as much as power carried by four AC conductors. And third important point is that cost of right of way, DC conductors, insulators, and towers are cheaper than AC. In DC systems, all these things are cheaper. We have discussed about right of way already, and number of conductors are less, and the insulators requirement is also less, and towers are also cheaper in DC systems. And as already discussed, when number of conductors are less, then obviously power losses will also be less. So we can say that power losses are reduced as there is less number of conductors used, about 67 percentage. And one more thing is that in previous videos also we have discussed, we have the absence of skin effect and reduces the power losses. There is no skin effect in HVDC transmission line, and hence the power losses can be greatly reduced. And corona effect and dielectric losses are also very less in case of a DC line. So this is again the same curve which is having additionally the losses incurred by the AC and DC line. So from the graph itself you can see initial cost of AC is less, initial cost of DC is high, operation cost of AC is high, operation cost of DC is less. When it comes for losses, losses in AC will be comparatively high and losses in DC will be comparatively less. Cost subdivision for a typical 2000 megawatt HVDC scheme. So already we have discussed earlier in all the videos which we have discussed earlier. So we are telling that HVDC transmission is very much suitable for bulk power transmission systems. So here I am speaking about a 2000 megawatt transmission system, that is HVDC scheme. So what are all the various costs involved? So the cost involved here, as already discussed, it is based on, very importantly, the two things. One is the investment cost, the other one is the operation costs. So the first comes the highest cost involved, that is the converter transformer. So it comes under the investment costs, and civil works and buildings comprises about 14% of the total cost. Again, it is also coming under the investment cost. And AC filters, we require AC filters for HVDC transmission systems. And also when it comes for control, control refers to operational costs, and other equipments will be using that, maybe depending upon the investment costs or operational costs. Erection and commissioning, again the investment costs. Engineering, again the operational costs. Freight insurance also, it will be coming under the operational costs, and valves, it will come under the investment costs. So this is the total breakup of a particular HVDC system. So we can see the investment costs plays a vital role in the total cost of the HVDC system. This is why we are telling that HVDC system should be used only in case to case basis. So we can see in practical approach, you cannot see as much as DC lines as much as we are seeing the AC lines. Wherever you are going on the roads, you will be seeing only the AC transmission lines. Rarely you will see the DC transmission line. Why we are not able to see the DC transmission lines? We are speaking about a lot of advantages, a lot of characteristics approaches, and also we are telling that HVDC transmission is the best when compared to the top the AC. But still, why we are using more AC transmission systems and why we are using the very less DC transmission system? We cannot say even in future this DC transmission system will completely outnumber AC. It is not at all possible. AC transmission system will be there in its place. HVDC transmission system will be supporting the AC transmission system in many different ways. That is our main important objective. Okay, so we cannot say that always DC is better in case of technical economics and all the other cases DC is better for long distance transmission. But we cannot have only DC transmission system. We cannot just like that remove the AC transmission system from our total system. So that is not at all possible. So let us discuss the next topic, that is the technical performance. So DC transmission has technical performance and it has some technical advantages which is as follows. The first technical advantage is that full control over power transmitted in either direction. So in the first video we have discussed that reversal is possible in case of HVDC transmission system. So that is what we are telling here, full control over power transmitted in both the direction. Bidirectional power supply is possible in case of DC transmission. So we can have full control over that. And second important favor point is that ability to enhance transient and dynamic stability in the associated AC networks. An HVDC link is connected between two AC systems. So this HVDC link will be supporting in enhancing the transient and dynamic stability of the AC networks which is connected to it. And third important point is fast control to the limit the fault currents in DC lines, which is not possible in HVAC lines. It will take longer time to damp the oscillations and limit the fault currents also. And fourth important point is the DC link shall be used as asynchronous tie, which can tie down the small variations in the system frequency of different AC system. So DC link, obviously we have discussed a lot about this interconnection of two different nominal frequency AC system can be done only with the help of HVDC links. And we can say that next advantage is that two large AC systems, when interconnected by AC link, may sustain instability. This also we have discussed already. But DC link may dampen the system oscillations due to its inherent short overload capacity. And selection of DC transmission mainly depends on the economic suitability, because in some cases we cannot invest more, we cannot just like that invest for based on these advantages we cannot directly prefer DC, because economically it should be suitable, then only we can be going ahead and using that. So apart from this, all this technical performance, we will be just comparing a single phase AC line and monopolar DC line, how these two can be directly compared. So let us assume that the size of the conductor is same in both systems and maximum system voltage to ground is also same. So let us consider IP be the AC current in the single phase system and ID be the DC current in the monopolar DC system. So as we are telling that both of them are having the same conditions, let me consider ID is equal to IP. Since the system has maximum voltage and is same in both cases, we can say VD is equal to root of VP, where VD refers to that of the voltage, DC voltage of the pole with respect to the ground, and VP refers to that of the RMS line to ground voltage of the AC system. The power transmitted through DC line, we know the DC power can be calculated as the product of voltage and current. So I can write the formula as PD is equal to VD multiplied by ID. So power transmitted through AC line, we know AC power can be represented as power is equal to VI cos pi. So here I can write it as PAC is equal to VPIP cos pi. So the ratio of DC power to the AC power is given by PD divided by PAC is equal to VDID divided by VPIP cos pi. So based on the already existing case, so this ID and IP will be getting cancelled, because we know that ID is equal to IP already we have assumed. What is the remaining thing? We have VD and VP. So VD and VP, let's go back and check what we have given. So VD is equal to root 2 times of VP. So substituting that VD is equal to root 2 times of VP, VP will be getting cancelled. What I will be getting remaining? I will be getting as 0 root 2 divided by cos pi. Let us assume the cos pi value as 0.945. I will be getting the ratio of DC power to AC power is equal to 1.5. Taking this AC power on the other side, I will be getting the answer as the power in DC is equal to 1.5 times of power in AC. So I can say that monopolar DC line can transmit 1.5 times the power and AC line can transmit for the same conductor size and the system maximum voltage. So this is one of the example where we are initially we have claimed that power transferability is comparatively high in DC. This is one of the basic example, like a monopolar system can carry 1.5 times greater the power than that of an AC line. So let us discuss the next technical performance of AC versus DC, which is the stability. Power transfer in AC lines depend on the angle difference between the two phasors at the two ends. Angle increases with distance, and hence the power transfer capacity of the AC decreases with distance. So from this graph we can easily predict, we can see the stable power in DC is constant with respect to the distance. There is no part is changing in that, but in case of AC, you can see it is constant to some particular level. After it crosses some particular distance, the power transfer capability is getting reduced. So when it is getting reduced, obviously the stability will be a question mark. And next comes the voltage control. So voltage control is in AC is complicated due to line charging and inductive voltage drops. Maintenance of constant voltage at the two ends requires reactive power control from inductive to capacitive as the line loading is increased. Reactive power requirements increases with the length of the line. So whenever we are increasing the length of the line, reactive power requirement is increasing. So we need to compensate the reactive power. So we'll be discussing in detail in the next video about this particularly. So DC converter station does require reactive power. So we cannot say only AC requires the reactive power. Even DC converter station also requires reactive power for line loadings, but the line itself does not require reactive power. But in case of AC, we can say that AC transmission line itself requires reactive power compensation. So that is the basic difference between the voltage control of AC and DC. And here comes the power transfer capacity of AC and DC. So this tabulation will give you a clear picture how based on the distance the capacity in megawatt for HVDC is different from the capacity of HVAC transmission in terms of a megawatt. So just take some few examples like for 500-kilometer distance, in case of a plus or minus 400 kilovolt, so the power transfer capacity is about 2250 megawatts. For the same case, for the same 500 kilometer, you check HVAC transmission in megawatt 400 kV, the power transfer capacity is only 405. Let's take this second example for the 500 kV, sorry, for 500 kilometer distance. If I'm using a plus or minus 800 kilovolt voltage level, then I will have a maximum power transfer capacity of 900 megawatt. For the same case, you just take the maximum level 1200 kilovolt. Even there, the power transfer capacity is only 5790, almost half less than the HVDC value. So let me take another example for 900 kilometer distance. We can see the capacity of in megawatt is 1460. For the same case here, the power transfer capacity is only 261, and you can see it is getting reduced. Why it is getting reduced? By with increase in length and increase in voltage, the power transfer capacity is getting reduced. That is not in case of the DC systems. So DC systems are always preferred when we are going for a head up or for higher distances. So that's all about this video, my dear students. So let us recall what are the things that we have discussed in this video. So initially we started with the economics of transmission, DC and AC. So economics refers to investment and operational costs. So when it comes for investment costs, the DC is somewhat higher and AC is comparatively less. But on the meantime, after the break-even distance, the DC cost is comparatively less. The AC cost is increasing steeply. That is what we have seen with the help of a graph. And also, we have discussed that the losses in AC lines are comparatively higher than that of the losses in DC lines. And we have discussed many technical performance of the DC transmission system like voltage profiles, stability, and all the other factors. So we will discuss all those things in detail in the upcoming videos. Thank you so much, my dear students.